Socratic Math Tutor here. So today we're going to talk about Questorials, which is a term actually I made up. And the idea here is that this is a family of numbers that is a lot like the factorials, but slightly larger and, in my view, quite a bit more mysterious. Now, I don't know what these numbers are officially called, so this is my own made-up name. Keep in mind they might be out there in the literature under a different name, but if so, I haven't heard of them, and that's why we're using this terminology. And the reason we're using quest here is just because we're going to denote them using n question mark, right? N factorial, as you probably all know, is n exclamation mark. And so question mark, quest, okay, that's where this name came from. So not too profound. I mean, that said, I think the numbers themselves might be a little bit profound. So before I tell you how they're defined, let's just list a few of them and see what they look like. I'm going to let n vary through the small whole numbers. Obviously, this diagram goes forever, but we can only depict a finite portion of it, so we'll go down to 5. And n factorial, as you probably know, is defined by starting at 1 and then multiplying by this number each time. So we multiply by 1 to get the next number, then we multiply by 2, then we multiply by 3, then we multiply by 4, and finally we multiply by 5 to get 5 factorial. And obviously this family of numbers goes on forever. So n Questorial will also start at 1. After that, it's going to jump up to 1.6180 to 4 decimal places. After that, we encounter 2 Questorial, which is roughly 2.2470. And I'll just quickly fill out the rest of this table, all the way up to 5 Questorial, which is roughly 120.775. So this list also goes forever. And although the items in this list aren't whole numbers, it turns out these Questorials actually kind of behave like whole numbers in a way that I'll make precise later in the video. Also, the more perceptive amongst you will probably have noticed that this looks suspiciously like phi, also known as the golden ratio. This is indeed phi, and so the Questorials, in some sense, are one particular generalization of the golden ratio. So I think that's quite cool. We've got both factorials and the golden ratio somehow involved here. And now what I've got to do is tell you actually how these numbers are defined and what I mean when I say that in some sense these are very close to being whole numbers, or let's say they behave like whole numbers. Now, to define Questorials, we should start by thinking about factorials. And we need to try and connect factorials with polynomials somehow. So here's how we're going to do it. Supposing that I multiply out, say, 1x times 2x times 3x times 4x, for example. Okay, this is obviously 1 times 2 times 3 times 4, which is 4 factorial, times 4 copies of x. So this will be 4 factorial x to the 4. So what that basically means is that if we try and solve x to the power of 5 equals 1x, 2x, 3x, 4x, we'll end up with this equation involving a factorial. And so we can solve this by moving everything to the left-hand side and then factoring things out. So when we do that, we end up with x to the power of 4 times x minus 4 factorial equals 0. And this obviously has two solutions, namely x equals 0 or x equals 4 factorial. And this actually lets us describe 4 factorial as the largest solution to a particular polynomial equation, right? So 4 factorial is the maximum x in R, such that x to the power of 5 equals 1x, 2x, 3x, 4x. And more generally, we can say that n factorial is always going to be the maximum x in R, such that x to the power of n plus 1 equals the product, as I ranges from 1 through to n, of I times x. So not really that profound, but does let us describe n factorial as the largest solution to a particular polynomial equation, which is kind of cool. Now, to make this profound, what we're going to do is we're going to take this formula and we're going to deform it slightly. So we're going to define that n Questorial equals, so we've still got max. The left-hand side of our equation remains exactly the same. The right-hand side still involves a product from I equals 1 through to n. But this time, instead of just writing ix here in the brackets, we'll put ix minus -1 to the power of I. Just like that. And what we're going to see later is that if we change any part of this definition, the idea actually doesn't work. So for example, if we make this a plus, it doesn't work. If we change this from -1 to the power of I to just -1, it doesn't work. And if we have +1 here, with either a plus here or with a minus, once again, the idea doesn't work. So there's something very special about this formula. And that'll become more apparent later when we look at some graphs and we actually try graphing these polynomials. So these have a very specific shape, and you're going to lose that shape if you try and play with the formula. All right, so let's get rid of everything except the definition, and we'll center it in the middle of our screen and kind of have a little play with it, see what we can make of this. Now, I claimed earlier that 1 questorial is the golden ratio. So let's just check that from the definition to get a bit more familiar with actually using this definition. So 1 questorial is the greatest number, x in the real line, such that x squared is the product as I goes from 1 to 1 of this expression. So we'll just rewrite that line. And we'll make the following change. We'll just plug in I equals 1 here. So 1x minus -1 to the power of 1. And this will simplify down a little bit. So in particular, this expression becomes x plus 1. And by definition, the positive solution to this is the golden ratio. There's also a negative solution, but that's not the maximum of the two. And so this must equal phi, essentially by definition. Now, for me personally, this formula is a little bit too complicated to really be that enlightening. I mean, it's important to have that explicit definition. I think that's really key. But once you've got an explicit definition like this, you need a way of getting your teeth stuck into it, because just staring at the formula won't do it, basically. So what we'll do now is we'll look at some graphs and we'll see if we can try and understand what this is really saying and how these numbers are related to the ordinary factorial numbers. Okay, so I've just fired up desmos.com, which is a free online graphing package. Let's start off by trying to understand 4 factorial in kind of the polynomial viewpoint. So y is going to be x to the 5 minus, and here we put 1x, 2x, 3x, 4x. And it probably looks like this polynomial does not have any x-intercepts except for 0, 0. But of course, if we zoom out, there we are. We have an intercept at 24 because 4 factorial equals 24. So to get 4 questorial, all we do is we copy this, and here we add +1, -1, -1, +1, and -1. And you'll notice that the maximum solution is just slightly larger than 24. And the other important observation here is that if we zoom into this area, all 4 of our other x-intercepts are somewhere between -1 and +1, right? So if I put x equals -1 here and x equals +1 there, you can see that all 4 of these solutions are between these 2 lines. And as far as I can tell, this general tendency to land between -1 and +1, it works for all the questorial polynomials. So for example, if we just get rid of that, and if we lower this down, so now we have an x to the 4 here, and we get rid of this last term, okay, this is the polynomial associated with 3 questorial. And sure enough, the x-intercepts lie between -1 and +1. And we've also got this larger x-intercept out here at a value of roughly 6.699, which is to be expected because 3 factorial equals 6. Now, I mentioned earlier that you can't really tinker with this definition too much without breaking the idea. And what I really had in mind there is that if we want these roots to be real, and we want them to be distinct, and we want them to live between -1 and +1, as far as I can tell, you can't really change up the definition. So for example, if we were to put a minus here, okay, all of a sudden we've got this root out here that is bigger than 1, which is not what we want. We want these 3 roots to be between -1 and +1. On the other hand, if we make all of these pluses, okay, now this is between -1 and +1, but it's no longer true that we have 3 distinct real roots between here. We actually only have 1 real root between there, and as far as I can see, Yeah, so as far as I can tell, this polynomial only has two distinct real roots, namely this point and that point. So because of this, there does seem to be something quite special about the definition. Now you might say, hang on, what is it that's so special about having the other solutions be between -1 and +1? Like, why would that actually matter? And this goes back to a comment I made earlier on in the video. So I said, well, these numbers are not whole numbers, but they kind of behave like whole numbers. And so it turns out that as long as all our solutions, except for the main one, are between 1 and -1, this number out here, which is our main solution, is going to have some really special properties that make it not an integer, but that make it integer-like. Now, to illustrate this point, we're going to need more decimal places than just 3, so Desmos won't cut it. Therefore, I'm going to copy this polynomial. We'll just copy this part, and we'll go to Wolfram Alpha, different website, and I'm going to set this equal to 0 and ask it for a really accurate decimal expansion for that solution we're looking for. So here's the solutions. I'm going to click approximate forms. Let's get more digits. Okay, so this looks pretty accurate. Actually, it turns out this is nowhere near accurate enough. We need much, much, much more accuracy. So I'm going to click this button a few more times. Okay, hopefully that should be enough. Click here on plain text, click here to copy, and I'm going to go back up to the top. What I'm going to do is I'm going to take this enormous, well, it's not really an enormous number, it's an enormously accurate number, and I'm going to raise it to a high power. So what we can do, for example, to the power of 30. And the problem is, once we raise this to the power of 30, it really will be enormous. And so what I'm going to do is just reduce it modulo, I don't know, 1,000 or something like that, just so we can chop off most of those digits and focus on what's happening on the right-hand side of the decimal point. Let's go ahead and see what the answer is. Right, and so check this out. After raising this number, which is clearly not a whole number, to a big power like 30, we end up with something that is very, very close to an integer. Right, so in particular, when we reduce this number modulo 1,000, the resulting number is very close to 700. And that number will change based on what this power is, but the fact that it's close to an integer won't change, and in fact it'll get closer and closer the higher this power becomes. And I'll just emphasize that it's not just this number that has this property of ending up close to an integer when you raise it to a high power. I'm pretty sure that actually all the Questorials have it. And if you're interested in learning more about why this is the case, the key phrase here is PV number. So this is a real algebraic integer greater than 1, all of whose Galois conjugates, these are the other roots, the ones that aren't the main one, all of whose Galois conjugates are less than 1 in absolute value, hence the importance of being between -1 and +1. And Wikipedia explains that it's a characteristic property of these numbers that their powers approach integers at an exponential rate. And unsurprisingly, the golden ratio is a key example. So that's it from me for the day. If you want to learn more about Questorials, you'll probably have to develop the theory yourself, because as far as I can tell, absolutely nothing is known about them. So if you have any cool conjectures, put them in the comments section below. I'm definitely excited to look more closely at these numbers when time permits, but for now it's adios.